Hi everyone. My name is Amir Naveh. I am head of algorithms development at Classiq. We are a quantum computing software company based in Israel. And I will be giving a talk on automation and synthesis of quantum circuits, which represent a radically new way of designing quantum circuits and algorithms. So a bit about our agenda for today. We'll give a little introduction about quantum circuits and current methodologies for designing quantum circuits, see the challenges in these design approaches, and then present a radically new way to synthesize and actually create quantum circuits, a bit of results and future work that we're working on now, and then maybe a little bit of an overview on Classiq in a more general sense. So let's begin. And first of all, I guess most of you are familiar with this, but currently, when we're talking about universal quantum computing, the most common way to design to create algorithms is in gate level circuits, right? So we see on the right-hand side part of a Grover's algorithm on 3 qubits, and then a quantum Fourier transform on the bottom part. And in essence, this means putting 2 by 2 and 4 by 4 unitaries on the individual qubits, and any general unitary operation can be done using these gates. These are the gate level circuits we're all familiar with. And then when we're talking about current design methodologies, how we'd go around designing quantum algorithms today. So generally, there are a couple of main frameworks. One is tuning existing algorithms. So a pretty comprehensive list is on the left here. Shor's algorithm, Grover, HHL, which are more accurate, and then VQE and QAWA, and of course, building blocks such as Fourier transform and amplitude estimation. Then you can also create novel circuits, right? Place the individual gates to create some desired functionality, and you can simulate the behavior on a small number of qubits using state vector simulators or others. And we have a few frameworks or software packages that allow this, right? So a circuit, in this example, we can see the gate level programming of a very specific circuit. And then we have Cirq from Google, and over here we can see also that we can put parameters on specific frameworks, right? And then put specific building blocks. So this is a quantum Fourier transform from Q-sharp from Microsoft. And all of these frameworks have a fundamental problem. So when designing quantum algorithms, we will soon be, or if we take IBM's roadmap, for example, we will be in thousands of qubits in 2 or 3 years and millions of gates. And the current methodologies do not scale. And the ability to create novel circuits is extremely limited. We can either tune the existing algorithms or create very, very limited circuits at the gate level. So when we're talking about what we do as a company, what Classiq brings to the world, we are solving this problem. And just to put a bit of orientation on us and where we position ourselves in the quantum software stack, so the level above the gate level programming and the building blocks and the tuning of the algorithms is the level of high-level modeling of circuit generation that allows us to do things at a much more abstract level. And that is what this talk will be focused on what are the technologies that enable this higher level of abstraction. So the motivation for the technology comes from what has been developed in the classical world for the past 7 decades. So when we're thinking about, for example, chip design, where you have to place billions of qubits of transistors on a chip, then of course you're not placing them manually. You're putting a description of how you want the chip to function, and then tools such as Cadence and Synopsys, for example, and many others are synthesizing these high-level instructions into actual circuits. And this is exactly what we're doing in the quantum framework. So first, we start with a model. that has a description of the desired circuit functionality. Then from this model, we synthesize circuits that comply with the model. And then finally, we can take the circuit, analyze it, gain insights, and then reiterate the model to incorporate our insights. And so I would like to dive a little bit deeper on how this is actually done in the underlying technology. So when we say a model of the circuit, what we mean is that we have some description of the circuit. And formally, in a mathematical sense, this can be seen as a constraint satisfaction problem. So constraint satisfaction problems are basically a list of variables, a list of domains these variables can have, and a list of constraints. And we'll see an example in a minute where we show what these how these variables, domains, and constraints can map into actual quantum circuits and solve actual problems that we have. And then the process of synthesis is to solve the model, right? So we want to find an assignment for these variables that satisfy the constraints. And once we have an assignment, if we did the mapping correctly, this is mapped to a specific quantum circuit, to a specific gate level quantum circuit. So we're starting from the model, which is abstract. It's not yet a gate level circuit. And from the model, which is a set of variables, constraints, and domains, we can synthesize a specific gate level circuit. So that was in very high level, and now we'll give an example to maybe give a bit of a better understanding of this framework. So on the upper part of the screen here, you see a very simple quantum circuit. This quantum circuit creates what we would maybe call an extended GHZ state, or simply a superposition of all ones and all zeros. And we can see different representations of this circuit, right? Different ways to describe it. So one would be maybe in a graph where the nodes are the gates and the qubits, and the edges are the connections between them. And then on the left-hand side, we can view this as a representation of a matrix where we have the rows representing qubits and the columns representing cycles. And then if we say number 1 is Hadamard gate and number 2 is a CNOT gate, then we can describe this circuit as placements into this matrix. So, and then we say, OK, but we don't want this specific circuit. We want only to keep the functionality. So we want to have this specific state, right? At the end, let's say we start at all zeros. We want to have at the output these two states. We don't care about the sequence of the gates, and we don't really care if we have a bit flip in the middle. We just want to create this maybe extended Bell state or GHZ state. So we can map this into a model, right? We can have our variables, which are which gates we put on each qubits, and they are taken from a domain of all possible gates. And we can have 4 2-qubit gates, which control qubits they have, right? And the options are all the different qubits. And constraints, for example, on a CX gate, we have exactly 1 control qubit. And we want to have, in the end, the linear entangler functionality on these 5 qubits. And then we can see we have different possibilities that comply with this constraint satisfaction problem. So we have the one we've seen on the previous slide, but we have here a different implementation, a different circuit that still complies with the same model, right? This is a different assignment. And then we have assignments that are obviously invalid. And so this gives a lot of flexibility on how to actually design the lower level circuit. And just to give another example that is maybe a little bit more complex. So for example, if you want to do quantum arithmetic within your circuit, and say you want to have a very simple expression such as a squared minus b squared, then you'd have many different ways of actually doing this. You can do it first by multiplying and then by subtracting, or first by doing the addition and subtraction and then by multiplying. You can choose if you want to use ancillary qubits and shorten the depth of your circuit, or if you want to use less qubits, but then you have a larger quantum circuit. So you have many parameters that are very hard to design manually, very hard to solve this by hand. And then these are, up until now, we talked about very simple examples to give an illustration. But actually, this exact framework can work for much more complicated examples, right? So when we want to build complex building blocks, such as oracles or complex quantum arithmetic problems, when we want to map certain system dynamics into a quantum circuit, when we want to have constraints on the circuit, whether it be hardware parameters such as connectivity or specific gate sets, or depth of a circuit, or error levels, or any sort of functionality demands we have from the circuit, these can all be mapped into the CSP framework, the constraints, variables, and domains framework, and then synthesized into a concrete circuit. And sometimes there are many circuits, and then we can optimize for a parameter of our choice. So what are the benefits of this approach? First of all, we have finally a flexible and scalable approach to designing large quantum circuits. So this is a radically new approach from what is available today, and it allows us to design quantum circuits that are not limited by what we can grasp and design manually. And this is maybe the largest benefit and the largest novelty we bring. And then also, once the low-level logic is implemented automatically, we can build much more complex circuits, much more complex logic inside, and also have better efficiency in design and optimize. And then also we can again choose what we want to optimize on, and then since many different circuits can comply with a single model, we can have a circuit best suited to our needs. So just to give a short survey of the results we've had so far with several of our clients and customers and design partners. So a framework for combinatorial optimization, where you can specify many different problems with the constraints and generate different ansatzes with different parameters. And also oracle generation, which we've talked about earlier, where you can design which exact functionality you want, and the oracle will be generated. So just these screens that I'm showing here, on the left-hand side, you can see the model of the circuit, right? The high-level description. And this is a specific instance of a circuit complying with this model. And then you have, in this case, it's generated on top of Qiskit. So you have quantum assembly, which is the specific gate level circuit with all the individual gates and the qubits they're applied to. And then this is just the beginning. So some of these we've talked about, but we're working on also on Hamiltonian generation and system dynamics, on custom constraints from users, on optimized resource allocation, be it number of qubits or the depth of the circuit, and handling of soft constraints and custom optimization criteria, and also hardware-aware constraints, which is a big issue, especially in the NISQ era. So quite a lot going on, and all this is possible because, again, this framework allows us to bring really new possibilities into quantum circuit design. So we're extremely limited now, and while this is still only the beginning, this, as we see it, is maybe the most possible or promising way to design quantum circuits today. Just for the short time I have left, I'd be happy to share more, obviously offline maybe, but at Classiq, we're a team right now of around 20 quantum software developers. Around half the team are quantum information experts, and the other half are quantum software developers that come from a background in more of classical development. And our team is dedicated to developing this specific product that allows us to abstract over the gate level and create novel quantum circuits. So I hope I've made things maybe maybe clear. And that's it. I'd be very happy if there are any questions or comments or remarks. You can reach out to me or the company. This is my email, and happy to take any questions. And again, thank you.